Good afternoon, all. So we start the third session. That is here. I want to introduce you, Professor Sarith Divakar M. He is assistant professor in Department of Computer Science and Engineering, LBS College of Engineering, Kasaragod. That is our institute. So he joined here in 2015, and he is doing his research in this deep learning, machine learning for agriculture applications also under Cochin University of Science and Technology, Kerala. He graduated from CUSAT, Cochin University of Science and Technology, and did his MTech from Mahatma Gandhi University. He is also a master trainer of artificial intelligence and machine learning course offered by the additional skill acquisition program run by Government of Kerala. So his research interest includes machine learning and deep learning in computer vision application. So I'm sure that you will be benefited out of this session. You can interact after the session. And he's moreover he's very dynamic personality, and he is doing many activities. He's pivot before behind many activities here, like industrial entrepreneurship development cell, then placement activities, etc. So let us start. I welcome you, Sarith sir. So we will start the session. So our session is handed over to you, sir.
Okay. Thank you, ma'am. Oh, my screen is visible, right?
Yes, yes. But you put it in slideshow. Okay, right.
It's fine, right? Okay.
It's clear. It's okay.
Yeah. Okay. Good afternoon, all. And in today's session, I'm planning to discuss about agriculture 4.0, and we'll be looking at the data analytics techniques. And in the end, we'll be having an hands-on session also that is related to data analytics. Okay, let's start with the challenges first. There are a lot of challenges that is faced by the agriculture industry right now. One of the main challenges is the population. The population is growing, and it is expected to reach around 10 billion in 2050. Okay. So that will surely boost the demand for food. Okay, right? And the farmers have to produce 70% of more food by that time. So that is a real concern. This is actually a report from UN Food and Agriculture Organization. And again, merely producing the food will not be enough. So the food should be customized to the needs of the growing urban population also. Now we have a lot of platforms to do that, but still there are a lot of food wastage. So we have to customize the needs to the urban population. And the next challenge is about the natural resources. And according to this report, 25% of the farmland is already rated as highly degraded. So usually farmers, from their experience, they used to do crop rotation and all. But according to this report, it's already degraded, and there are around 40-50% of the farmland which is slightly degraded. Maybe we can get something out of that. And at the same time, it's worthy to note that the water resources are also getting highly stressed, and you can see the investment $1 trillion investment is necessary until 2050 for irrigation water management, especially in the developing countries. Okay. So these are actually the real concerns. And the climate change is also another concern, like the greenhouse gas emissions has grown 2 times for the past 50 years. And now what this greenhouse is actually doing, like it's tap heats and it's causing the climate change also. Okay. And we also witnessed all those floods here in Kerala. That means the frequency of these floods, droughts are getting increased. So all these trends actually is leading to reduced crop yields, which is a big concern. So considering the growth of population. Another real challenge is about the food waste, and you might not be knowing, like the 33 percentage to 50 percentage of all the food produced globally is never eaten. So that's a staggering figure actually. Like, and also it's actually bad for the environment when you consider the case of greenhouse emissions from this food if it is not properly decomposed. So all those concerns are there, and how we are going to solve these challenges, like the population, the climate change, the food waste. Okay. So the solution is actually agriculture 4.0. And before going to see what exactly is agriculture 4.0, anyway, you might be knowing about the industrial revolutions, and right now we are in 4.0. In the same way, the agriculture is also in 4.0. So let's look at the agriculture 1.0, 2.0, 3.0 first. Then we'll come to agriculture 4.0. In the agriculture 1.0, right, we were using manpower and animal forces, like in the traditional agriculture era, but still we are using animal forces and all, manpower also. But no, it has changed a lot, especially in developed countries. And by the 19th century, with the introduction of steam engine and all, no, the agriculture 2.0 is actually powered. And but the issue is that a lot of chemicals were used, which is actually harmful to the environment. And then comes the agriculture 3.0 in the beginning of the 20th century, with the introduction of robots, like the invention of computers, and the rapid development of electronics. All those actually contributed to agriculture 3.0, and the deployment of robots in the field. So that helped a lot in the agriculture sector. And programs that have been developed to automate a lot of machineries, and this actually resulted in efficient usage of resources and all. And also a lot of optimization is also introduced, but not much in 3.0. Like you can schedule the irrigation based upon some algorithms, and you can also reduce the use of chemicals by using some data mining algorithms and all. So all those things were in agriculture 3.0. Right now we are in agriculture 4.0, and we generally call it as smart systems, smart devices, and with all the technologies, like Internet of Things, which is actually the topic of this FDP, and big data, AI, cloud computing, remote sensing. All those technologies contributed, and right now we are in agriculture 4.0. So when you talk about the IoT, like it actually reduced the cost of the systems that is developed, like machineries and all. No, like you can use IoT concepts to reduce. I mean, to build a low cost sensor. You don't have to do all the processing in the machinery itself, right? You can have a communication channel, you connect to cloud, you can do the computation there. So all the IoT in turn actually helped a lot in agriculture 4.0. And big data, coming to the big data helps to give insights to the stakeholders. It can be farmers or any other decision makers. Again, big data actually use machine learning, deep learning algorithms. And as I said, IoT devices send data to cloud, and the cloud computing is getting cheaper nowadays. So the overall cost of the systems is also better. And with the remote sensing, that is also contributing a lot. Now, you don't have to go for proprietary data from the companies. Now, through Google Earth Engine, actually, you are getting all this remote sensing data free of cost. Like uh, there is a Modi's instrument by Terra Satellite. What you can do is you can simply write a simple JavaScript code, and you can fetch all the remote sensing data into your Google Drive. So it's available free of cost also. So all those things actually contributed to agriculture 4.0. Now, let's look at a scenario where all these are actually useful. Okay. So here you can see we have a simple greenhouse, and you have a lot of sensors. Then the IoT devices connect those device sensors to the cloud computing environment, and all those computation, all those feature engineering. Maybe you need some pre-processing also of the data. All these things can be done in the server side or in the cloud side. And the results are sent to the farmers, and the farmers, if they have smartphones, they are getting the results in the smartphones. And if they don't have any smartphone, also maybe the test-based SMS also can be received. So overall, these kind of systems, it optimize the production efficiency, also the quality. And as we have seen the challenges, the climate challenges and all, uh, this kind of systems can surely minimize the environmental impact. So we are actually going forward with the sustainable systems. So I'll show you a simple a video that's from the Australian government to have a real look at the agriculture 4.0. Um, please just confirm whether you are able to see it.
Yes,
What about the audio?
audio is not coming. Video is playing, no audio.
Okay. Okay. Anyway. Okay. So the essence of that video is see the Australian government actually providing a lot of grants to the researchers to solve the real agriculture problems, and also they actually highlight the importance of the farmers, industrialists, and also the researchers to collaborate together and to develop sustainable systems. And we have seen a lot of technologies in that video, like the robotics, the automated equipment, satellites, all those things. And let's have a comparison now between a small scale farm and a smart farm. So the precision agriculture, and nowadays we can generally call the entire thing as a smart farming. Okay, so in the traditional way, we don't have any kind of internet of things set up, and we were using mechanical technology or like some kind of analog devices and all. But right now in the smart farming, we have internet of things, and no sensing was available. We have a lot of low cost sensors available now, and we usually don't store any kind of data or records. That's actually a real concern, especially in India right now. Not much enough data is actually collected through farms, so hopefully in the future we'll be doing that. But in US and all, they are actually collecting a lot of data now, which actually contributes to the big data. And in the case of manual labor, which actually been replaced by robotics, and the hand or animal power is replaced by automated equipment. The difference is that in robotics we have some kind of intelligence in it, and in the automated equipment is like a simple automation of some portions. And the farmer experience is, like I said in one example, like the crop rotation. So it's actually based on the farmer experience. But if you can collect all those historical data, and if you can use remote sensing satellites, GPS and all, we can actually induce the intelligence in our system. And the summary is like all the smart farming systems is really driving the agriculture 4.0 revolution. And one thing I want to highlight here is like even though we don't usually collect all those sensor data using, because still it's some of the sensors are very costly, but we can still use all those remote sensing images, which are actually freely available throughout the world. That is one of the area where you can actually work on a research problem. And what you exactly need is you need some kind of data about the crop, which is actually available, like maybe at the district level or the state level. So such data is available. For example, the crop production data or the crop yield data and all are available through the Ministry of Agriculture department websites. So we can use that, and we can also use remote sensing images, which are freely available to develop systems. Okay. That is one suggestion. Now coming to the agriculture 4.0 applications, we can divide into mainly 4 domains. In the monitoring, it's like we have crop monitoring systems, develop soil monitoring systems, and in the so control weed, pest, disease control systems, and you can take actions also based on that. And the predictions, like the agriculture production yield, and logistics also have a lot of opportunities in agriculture 4.0, like supply chain management. And we can actually divide all those technologies into different layers to get real insights about these technologies. So in the physical layer, there actually all the sensors and these actuators comes, where the sensors play a key role in collecting the data, and this actuators and use some kind of control systems or microprocessors to take actions based upon the data that they are getting from the system. And in the communication layer, we have wired or wireless communication. And in the service layer, you do all this kind of data analytics, visualization, or the decision making. We generally call it as decision making systems. And these actually give insights to the end users, which are actually stakeholders, can be like farmers and all. So application layer will be giving all these reports, maybe in a mobile phone or in other website environment. So we can also have some other kind of external source also fed into this service layer. Like the service layer can be in a server, or it can be in a cloud also. With that, we are slowly moving to the data analytics part. So as a summary, we as a user is getting all the insights. We start from the sensing part. You have the connectivity parts, and you can categorize it under IoT. Then the cloud computing will do all the storage. You have to do some kind of pre-processing, like if the data is not readily processable, you can have to do some kind of pre-processing. We'll discuss that. And in the data analytics part, we have big data. Usually, a lot of data is getting generated now with all these IoT devices, billions of IoT devices. So we generally call now it as a big data. And we use AI and ML algorithms to do all the analysis. And the decision support system will take the decisions based upon the results obtained after training using AI and ML algorithm, which is forwarded to the user. And maybe in some systems, you can send back to this education systems to take some actions. Okay. These are the core technologies in agriculture 4.0. Now, coming to AI and ML algorithms. So let's have a clear look at what exactly this AI ML algorithm is doing. What is the role of AI or machine learning algorithms, artificial intelligence or machine learning algorithms, the role of AI ML in agriculture. So before that, let's look what exactly is the learning process. So you can say learning is a kind of algorithmic way of making sense from data. So in machine learning, it's all about data. So data, it can be images, it can be numerical data, or any kind of data. So these algorithms is an algorithmic. I mean, this machine learning algorithms is a way to learn from the data. Okay. So why we are saying it is learning? So learning means you are improving with experience. So we'll take an example now. We'll take this example, like there's a plant in an environment, and maybe it can be a controlled environment. There won't be any precipitation there, and there is evaporation, there is transpiration. We combine that and we call that evapotranspiration, and we want to find out the rate of this evapotranspiration. Okay. So according to Tom M. Mitchell, is actually a American computer scientist. So a computer program is said to learn from experience E with respect to some task T. So the task here is to estimate evapotranspiration rate. Okay, we have to find out. So once we are able to find out this evapotranspiration rate, then we can decide whether we want to irrigate the plant or not. That will be our decision. Okay. So the task is to estimate the evapotranspiration rate. Now, what is this experience all about? The experience is the learning experience from a data set. Okay, so which data set we will be using for this evapotranspiration? Okay, so you can think about a data set where we have some information about the climate, like it can be temperature, one of the feature. It can be type of the plant, because for different plants, this evapotranspiration rate will be different. Or you can consider relative humidity. You have a data set of that, and also you have the corresponding evapotranspiration rate, which is actually recorded. So that is your experience. So when you have more and more data that is fed to this data set, to the learning process, you can improve your performance. So we use a metric to measure the performance. It can be an accuracy metrics or it can be some kind of a measure you want to find out a rate, maybe the evaporation rate, and you can use some other metrics like root mean square and all. So anyway, the overall essence is that the learning process improve with experience at some task B, and we measure the accuracy, and we feed more and more data, and we use many kind of algorithms, many kind of techniques to improve the accuracy. So that is the essence of this AI and ML algorithms. Okay. And once you get the results, once you get the insights, then you can take the decisions. Like in this example, you can take the decision whether you want to irrigate that plant or not. Okay. Now, basically, these machine learning algorithms or data analytics, you can divide into two types. It is predictive analytics. It is descriptive analytics, or we can also say predictive analytics as supervised learning, and descriptive analytics as unsupervised learning. Okay, so let's take an example now. So what this predictive analytics actually doing? So here you can see we have a data set. So in the data set, we have a lot of fruits. Okay, so information about the fruits. So the information is the freshness of the fruits. Okay, and also you have the price of fruits. So it's in Indian rupee, say 0 to 100. Okay, so that is your as is, you can consider you have simple data set. Okay, you have two columns here. You have the fruits name. So these are our samples. Like you have apple, banana. Okay, so different fruits are there. Okay, different types of fruits are there. And here for each fruit, you have corresponding freshness. Okay, so you have say freshness. Maybe you can scale freshness in days. So here the metric that we are going to use for freshness is in days. Okay, so you have values here, say 2 days, 3 days, 4 days. Okay, now you have one more column here, and that is your target, that is the price. Okay, so you have price, say 20, 10, so corresponding to each fruit. Okay, so with this data set, our aim is to find out, say you got a new fruit. Okay, like you got a new apple, and you know the number of days, you know about the freshness of that apple, and you want to predict its price. So that is our task. Okay, so this is our task, and we have our data set of this freshness of fruits and also the price of the fruits. Okay, so why it is called predictive analytics, or why it's called supervised learning? That is because you already have the information about the price of the fruit. Okay, you also have the information about the freshness. So we can say this price is a dependent variable y, and x is a independent variable, and you can form a relation like y, you can form a function y is equal to f of x. Okay, so that is actually a kind of a supervised learning. So you have information, so we then call that as a label. Okay, so that is a supervised learning. And as I said, when you get a new fruit, you can make the prediction. Okay, now take another example. So here I just taken an example from an iris plant, so which is actually a popular data set in machine learning and all. And here you can see there are 4 features. So it's an image of iris plant. Okay, and there are 4 features, that is sepal length, sepal width, petal length, and petal width. Okay, and we have a class label. So here class label means they are three different kind of iris plants: Setsoa, versicolor, and virginica. These are three different categories of iris plant. Okay, and these are the number of samples. Say we have 150 samples, and we have 4 features. We have 1 class labels. Now, this is our training data set. Or you can take, say, 100 samples from this. Okay, you take that as a training data set. Okay, and you can use the supervised learning techniques to build a model. Okay, and assume you have a model ready. Then when you get a new picture of this iris plant, you can use that model to predict whether it belongs to Setsoa, versicolor, or virginica. Okay, so these two are examples of supervised learning. So, given a very small summary of that, and this technique, the first one, we can call it as a regression technique. Okay, because here we are predicting something, predicting a real value. Okay, you do the training here, and once the model is ready, you do the prediction. You make the prediction. Here also, you are predicting, but the prediction is one of the classes. So we call this as classification. So this is a classification technique. Okay, so we have two kind of supervised learning techniques or predictive analytics techniques. So it is regression and it is classification. Okay, I hope this example is clear to you. And also some of the terms that I have used, I will be using that again in coming slides. Okay, so these are the features, these are class labels, these are samples, or you can say observations. Okay, and usually when you build a model, we divide into train and test data set, and use a training to build model, and use test to test the performance of the model. And when you test the performance of a regression model, you can use a metrics like RMSE, sorry, yeah, root mean square error, or mean absolute error. There are a lot of metrics available to test. Okay, so I'm going to do a testing for this data set. Okay, I'm going to plot a figure here. I got a banana, and the banana, say, is say like maybe say 30 days old, for example, 30 days old. Okay, so the plot will come here. Okay, now this is your x value of the new banana, and you can draw a straight line here. Okay, and this will tell you the price of the banana. Okay, so it's a say 6 rupees, something like that, for example. Okay, now as I said, you assume that you kept 70% of the data for the training purpose. Now you can actually do testing with 30% of data, or it can be a 80-20 ratio. It's up to you, and you do testing of all those 30% of the fruits. Okay, so you have a lot of predictions here. Okay, and the model, the regression model, maybe if it is a linear regression model, it will be drawing some kind of straight line here. Okay, and what exactly you are going to do the testing here? Okay, so the testing is about when you make this prediction. Okay, so once again I'm making it clear. So I'm going to draw a straight line. That is your model now. Okay, okay, so this is my model now, and when you get a new sample, okay, I'm going to use only points now, so otherwise you'll get confused. Okay, so there are a lot of test data that is coming now. Okay, we have 30% of the test data, and all these are predictions, these points, and when you connect that to this y-axis, these are the predictions. Okay, but since it's a test data, you already have the actual price as your class labels. So sometimes the price will be around here, sometimes the price of banana will be around here, sometimes around here. Okay, so this is actually the error. Okay, so there are measures like mean square error and all, so which will actually which will actually square the errors, take the mean. So, and finally you'll be getting some values like say 2.3 something. Okay, not going into those metrics in detail. So that's a kind of a regression model, and the way you find the performance of the model using mean square error, and you can improvise if you have more hyperparameters to tune. You can improvise the performance of this model, and you can try to reduce the error. So this is a kind of a regression model. Now, in the case of classification, we have different kind of metrics like accuracy. It's like so you made some predictions. So out of 10 predictions, you made 7 correct and 3 were wrong. So your accuracy is only 70%. Okay. There are many other metrics like precision, recall, and all. So that is a kind of classification problem. And what is our aim? You have to improve the accuracy. You have to improve the accuracy from 70 to 80 to using many techniques. So that's all about the supervised learning techniques in machine learning. Now coming to the unsupervised technique, and we generally call that as descriptive analytics. Okay, so it is actually getting patterns from the data. Okay, so we will take a simple example here. So you have a bucket full of fruits. Okay, and you want to group these fruits into 2 categories. Okay, we can do group into 2 categories. Okay, so here in the case of supervised learning, they say you have some information about your data. Okay, like your apple, mangoes. Okay, some information about the data. Okay, and like I'll just put color red, and say red, green apple, banana. Sorry, it's not mango, banana. Say yellow, for example. Okay. So assume in your training, so this data is not available. Like you don't know whether it's an apple. You don't know anything about the kind of fruit that you have. You only have the information about the color, for example. Okay, so in that case, how you will group these items? Okay, so like if you can do one thing, you can group all the apples together, and you can group all these bananas together. So we have two groups. So it actually grouped based on the color. Okay, so in this descriptive analytics point of view, we actually use a metric that is called distance metric. Okay, so we actually look for the dissimilarity. Okay, so how you will convert these colors? So maybe you can do some kind of coding, encoding. So you can put some values, say 1 for yellow. You put some different colors like say 2 for green and 3 for apples. Okay, maybe if you do in that way, and if you do in that way, and you can use the dissimilarity matrix and to group these items together, like you group these bananas and apples together. Okay, or like put like 1 and say 4 or 5 for this mobile encoding. Okay, anyway, we will not be we don't have to worry like you only have one feature. Usually there are a lot of features when you do this unsupervised learning. It's not about colors. There can be weight of the fruit, and the shape of the fruit. Lot of features will be there. All these are features like you have x1, x2, x3, xor, and you have the dissimilarity matrix, which will help you to actually group these 2 items into different groups. Okay, so that's about this unsupervised learning. So here we don't have any target label like whether it's an apple or banana, but based upon some features, we are grouping it together. Okay, and another examples, you have a lot of fruits here, and we use a technique called hierarchical clustering technique. Okay, uh, here you can go for a technique called clustering. Okay, and what it does is initially all these fruits belongs to one category. Okay, they are fruits. Okay, and when you do iterate over this algorithm, okay, at this particular point of time, you have 2 categories. So one category, that is you have, so if you can draw a line here, Okay, so you have banana, and you have all other falling into another category. Or when you draw a line over here, so in this case, okay, you have a lot of categories here. Okay, banana, tomatoes, plums, grapes, and cherries belong to one category. Strawberries, okay, peach and orange belongs to one category. And when you draw a line over here, you can see bananas one category, tomatoes in the category. All these plums, cherries, grapes, and strawberries belongs to one category. So you have total 4 clusters or 4 groups, and depending upon the algorithm. So you can stop the iteration where you want. Okay. So again, this is also using a measure called dissimilarity measures, as I said before. So this kind of technique is actually called descriptive analytics. So later we'll be seeing case studies using these predictive analytics as well as the descriptive analytics. So that's overall sense about this unsupervised learning technique. Now, okay, we'll be having a simple Q session now, only 3 questions. So you can go to this website, that is mendy.com, and you can use this code 66398703 and answer the questions. Okay, so I'll be waiting for 2-3 minutes for you to join first. So just go to www.menti.com and use this code. Yeah, I can see some of you are joining. Okay, I think we have enough participants. Still, participants are joining. Okay, so let's start. So the first question: estimation of precise amount of water required in a farm based on sensor data like humidity and soil moisture. So which kind of technique you will use? Yes, yeah. Most of the participants have answered correctly. It's a regression because here we want to estimate the precise amount of water required, right? So it's a target that you want to estimate. So it comes under the regression. Unlike classification, it's like a category. So it's not like you can categorize water into different groups. Okay, maybe some different techniques is there, like if you have three set of categories, set of values that you can set and make it a classification problem. But generally when you look at this question, it's clearly a regression problem. Okay, similarly we'll be looking at some other different problems also, so try to answer fast, we'll be getting more points for that. Okay, so I can see yeah, Amanda is scored maximum points because she answered first. So the next question. Identifying grape leaf disease from images captured using Raspberry Pi compatible camera. Yes, very good. So many of you have marked it correctly. So here we know you have a data set where you have labels and you can classify the grape leaf diseases. Okay, assume you have label that. Okay. Anyway, when you look at this problem in generic, you can see that it's a classification problem. Okay. So going to the next question. Okay, grouping farms based on crop yield. Yes, yeah. So most of the student, participants, they have marked clustering. So that's the right answer, because like you have farms with low yield, high yield, and you also have some other information like the productivity, the size of the farm, all those information, and you can use the clustering technique to group farms based on the crop yield. Okay, so very good to see that. So let's see the final leaderboard. Yes, congrats, Sangeeta, for answering correctly and getting highest points. Okay, so coming back to our presentation. So we have already seen what is supervised and unsupervised learning techniques, and now we'll be looking at some details about deep learning techniques, because nowadays, you know, you have a lot of images that is getting captured in whether it is in a farm, or you have a lot of remote sensing data or data captured using drones, and all those images images now we usually don't go for much image processing techniques recently now because with the popularity of deep learning techniques, all those feature extraction that you were actually doing through all those image processing techniques is nowadays not that much necessary. Okay, so you can avoid all those things with the help of deep learning techniques. So for the sake of that, I will just introducing the concepts of deep learning also, and we have some case studies that is using deep learning. Okay. So deep learning basically you can think like it's it's a kind of a universal function approximator. So like you have a function y is equal to f of x, okay, and this function can approximate everything in that sense. Okay, so the backbone of this deep learning techniques are neural networks, and you can use these neural networks, and also there are algorithms. Simple neural network I'll draw here, and there are algorithms like backpropagation algorithms that will help you to learn, and finally the function approximation. Okay, and the advantage of these deep learning techniques is they can actually learn any function. Unlike we don't have the much mathematical background corresponding to deep learning like other machine learning algorithms. So other machine learning algorithms like I'll give some examples. We have support vector machine, we have naive Bayes algorithm. Okay, there it's actually based on probability, and here we have linear algebra. Okay, and all those calculus, algebra, calculus, and all. So we don't have much mathematical background corresponding to these deep learning algorithms, but doesn't means we don't have any kind of mathematical calculation. Anyway, we have to compute gradients and all when you do the backpropagation and all. But still, there is an issue regarding deep learning, which is interpretability. And most of the researchers were not going for deep learning because you don't understand how it actually learning. But recently, a lot of studies have happened in deep learning, which actually give some interpretation. Like for example, you have an image of a flower. Let it be, say, a simple flower. Okay, and when you use a deep learning technique, so it's some kind of abstractions. Each layer in deep learning do some kind of abstraction. So maybe the first layer in deep learning will learn about the edges. Okay, and the next will be looking a little make more detail about this figure, like it will be looking at some petals or some kind of sepals, for example, and the next layer will be looking at maybe some part of this flower. Okay, so when you go to the higher levels, getting more and more details about this flower. So it's a kind of a abstraction. So we have now a lot of interpretability about these deep neural networks, and that also is actually the work of many Nobel laureates. I mean, I'm not say sorry, I'm not Nobel laureates. So it's a Turing Award winners like Lei Kuan, Yoshua Bengio, and all. So their contributions actually made this deep learning much popular. So the overall nowadays, like deep learning can approximate any function. Okay, so and also a lot of complex deep learning models has been evolved recently, and with the increasing computing powers, because we are for the past 20 odd years, we know that computing powers has improved a lot, and that's actually one of the drivers behind popularity of deep learning. Okay. Now let's see some of the very basic components in a deep learning scenario. So this is a simple deep neural network, or you can say like it's a deep feed forward network. Okay, and this is a iris flower classification problem. Unlike the category of iris flower classification problem that we have already seen. So here the classification problem is just to classify this iris. Whether it is an iris, whether it is not it's not an iris. So we can call this a kind of a binary classification problem. Binary classification problem. Okay, so these are the features: petals, sepal, and yellow patch, and veins. Okay, so we'll be looking at these features of all the flowers, not only iris flowers. You have, say, a data set of, say, 1 million flowers, for example. Okay, it's a very large data set, and you have to train a deep neural network from the data set. Okay? And your aim, your task is to identify whether it's a iris or whether it's a not iris. Okay? So these are the features, and you are feeding these features into the input layer of this deep neural network. Okay, so we have 4 features, so we have 4 input layers. Remember, in this particular problem, we are not actually sending these images. So we are doing some kind of pre-processing and getting information about the petals, sepal, yellow patch, like whether yellow patch is there. It can be a categorical value of also yes or no, or 1 or 0. Okay, and another concepts in deep neural networks is called hidden layer, which will help you to introduce non-linearity in your learning process. And there you have this activation functions. So there are a lot of activation functions in deep neural network, like sigmoid activation function, and recently we have ReLU activation functions. So the purpose is to introduce non-linearity in your learning process. And we have output layer here. So the aim of the output layer is to make the prediction, and we will be having a label data. We will match our predictions whether it's correct or not. If there is a if there's an error, the error is back propagated and using many optimization techniques, and we'll be using a function called loss function for that. And the optimizer aim is to reduce the loss. Okay, so there are a lot of loss functions available. For example, you have a mean square error a loss function in the case of a regression problem, or a binary cross entropy. So we'll be doing a hands-on experiment today, which use cross entropy, binary cross entropy for a classification problem. Okay. And the aim of this optimization function to reduce the loss, and you can do the training, and finally you'll be getting an accuracy of the prediction. Say like 90% of the time I predicted correctly, like whether it's an iris flower or not iris flower, and 10% there is wrong prediction. And there is a different techniques other than accuracy. You can actually go for precision recall. So we'll be looking at that when we discuss how to solve a real agriculture problem using machine learning. Okay, and again, there is a technique called hyperparameters. You have a lot of hyperparameters that you can fine tune and improve the performance of your model in deep learning. Okay, so that's the overall essence about deep learning. Okay, now let's look at a project now. So assume you are going to do a project for your agriculture problem. It can be say any kind of problem, like you want to identify, say, diseases in apple. Okay, so you have an apple data set. You have a lot of features, or if it's a deep learning problem, you have images of different apples, and you also have the corresponding labels also. So this is having a disease, maybe the type of apple diseases also, like type 1 disease, type 2 disease, type 3 disease. Okay, so it is a data set that you have. So you are given a problem. The problem is to find out whether which kind of apple disease it is. So that's the problem. Okay. So according to Andrew Ng, is actually the co-founder of Coursera and a former head of Google Brain. So all those machine learning and deep learning problems is actually a threefold. So you have the idea. Okay, so the idea is how we are going to solve this problem. And once you have this idea, like how we are going to solve the problem, like you get the data set, then you do some feature engineering if required, and you have to do some kind of pre-processing if necessary. Okay, and you build your model so that you code it, you build your model, and once you do that, then you can experiment your results, like whether you are getting the accuracy, or like if you expected accuracy, you have a problem, you are getting whether like a 70% of 80% of accuracy. So if you are not satisfied with this result, then you can go back to this idea stage again. Maybe there will be some problem with the idea or the data that you have, or you can no, you can, if you think that this actually, say for example, you are going to find a approximation, there is no dependence between these two variables, then you can simply throw away this idea also. Okay, so basically this machine learning or deep learning is an iterative process. So you don't expect it to work for the first time. Okay, you have to make some tweaks and you have to iterate it over and over again, especially in deep learning problems. You may have to change the configurations a lot until you get a best results. So start off with an idea, implement the idea in the code, then carry out the experiment and see how the idea worked. And if you think that there's a chance of improvement, make some modifications and iterate it again and again unless you get the best result. So that's the way to solve a problem. Okay, now say we are going to look in detail about how to solve this aggressor problem. So we have seen we can start from idea, you just code it, and you see the experimentation. Okay, so the first question that you should be asking in this case, you got a problem. I'll give a very simple example. So you want to predict the price of Apple. You want to predict the price of Apple based upon the color. Okay, based upon color. So that is a problem in your hand. Okay, so you have to ask yourself whether it's a real machine learning problem, and if there is no dependence between the dependent variables, so it is a dependent variable and color is independent variable. If you don't find any dependence, it's a very hard problem. Better you don't go for that. Okay, but if you are able to get some kind of relation, we can do some kind of technique, like there's a technique called correlation analysis and all, to understand if there's a relation between the variables. Okay, so like take another example, price of Apple based upon, we have already seen, like freshness, weight, etc. So there is some dependence. So then it's an easy problem. You can configure this machine learning problem, say like y is equal to f of x. So that's the first question you should be always asking, whether the problem in hand can be solved using machine learning or not. And the next question, the kind of scenarios that you should be using. And we have already done a quiz program based on that. You are given a question and you have to find out which kind of technique you will be using, whether you will go for a supervised learning technique like classification or regression, whether you will be going for a unsupervised kind of learning technique like clustering and all. So that's the next question that you should be asking. And the next one, the appropriate model that it should be. So we didn't discuss much about the different kind of classification, regression, and supervised learning models. So first of all, you have to look at the data size. Okay, so that's why I thought of discussing the models in detail here, because it actually depends upon the kind of data set that you have. So say you have a very small data set, then better you go for a linear model. So if you have a small kind of data set and you want to solve a regression problem, okay, then you can go for techniques like linear regression. Okay, it can be based upon technical ordinary least regression techniques and all. And suppose you have a very large data, then you better go for non-linear techniques. Okay, I'll give you an example. Say you can go for a technique like support vector machine. Okay, if you have a kind of nonlinear data, or you can go for multi-layer perspectrons and all to solve this nonlinear data. But there is another take on this actually, that about this non-linearity and linearity of your data. Okay, so like I'll give you a very simple example, like a simple classification problem. You have say, for example, you have apples here, you have bananas here, and this is a kind of a classification problems. And if you are using a simple linear model to divide this into two classes, you can simply draw a straight line like this. So it's a kind of a classification problem. But when you have a data set something like this, apple, then banana is this interchangeably, okay, because there are a lot of features, and you cannot actually go for a simple model. Maybe you have to go for this actually non-linear data, and you may have to go for some other non-linear problems. You may, if you see in XVM, you actually transform into another feature space and solve this. So there are a lot of complex things about that. We have techniques like SVM ML, multi-layer perspectrons, or you can also go for deep learning techniques, deep feed-forward networks and all. Okay, and there will be some scenarios in your data set where there is imbalanced data. So in the case of imbalanced data, you don't your model will not be working properly. Okay, for example, assume that you had to identify, say, whether a class of flowers. Okay, or you can think, or we'll take the same example of iris. Okay, we have versicolor, virginica, okay, and Setsova. And usually, see, in the actual data set, the contribution of each class levels is 50-50. So it's a balanced data set. Assume that you got an imbalanced data set. Like the versicolor is say 140, you have 5 virginica and Setsova. This is actually an imbalanced data set. When you try to build a model using this data set, and most of the time you'll be getting an accuracy at 98%. Okay, because you can see that the particular class labels or C color is having 140 samples. Okay, but the 2% is very important here. The reason is because you're actually missing these two important classes. Okay, so this accuracy is not actually a good measure if you have imbalanced data. So you would need some kind of a treatment to make these minority classes. There are many techniques to do that, to make this data set balanced. Okay. So that's about the appropriate model that you should be choosing. Now about the enough training data. So if you have more and more training data, you can surely improve the accuracy of your model. Okay, that's another thing, especially in the case of deep learning. If you have more data, you will be generalizing your model well, and there is different kind of problems that may occur if you have a limited number of data. Like you may try to overfit your models, like when you have a classification problem like this. This is apple, then this is banana, for example. And there's one banana over here. Okay, I'll use different colors. This is one banana over here. Okay, and these are apples. And if you have a less number of data set, there's a chance like you will be building a model. So for the classification, like this. Okay, which this can be a simple outlier. Maybe it may not be by mistake, maybe marked wrongly or some other things. But if you are building a model with very less number of data set, and there's a chance like you may overfit the data, and when you make the prediction, and say for example, you got your feature values like a banana here, sorry, apple here. Okay, for example, apple here, you may be treating it as a banana. So you don't enough data, there is a chance for overfitting. So the more the data you have, you can generalize the model well. And always start from simple models, then you can increase the complexity based upon the performance. So that's the thing to keep in mind. Also ensure you don't overfit to the training set. So for that, you can divide your data into training test set, and always see the test accuracy of the model. And sometimes when you're working with image data set, there is a chance like you build all the models using the images from the same distribution, like you captured it using a Raspberry Pi compatible camera, and you tested it, you got 95% the test accuracy. But when you try to predict from a real time problem, you captured using your mobile phone, and you are not getting the expected results. That can also happen, like if the distribution of the images are from two different cameras. So that can also happen. So that also you have to keep in mind. Okay. Now moving to the feature quality. This is very important when you are working in a problem. It actually depends upon the kind of features that you'll be using to build your model. Okay, so you want to build a problem to, for example, to predict crop yield. Okay, so in that case, you have to identify what all features contribute to this crop yield. Like you can say, for example, say temperature, humidity, wind speed, etc., etc. A lot of climatic indices are there. Okay, so you have to identify which all features contributes to your yield. Maybe you can do some kind of a correlation analysis and find the difference between each feature and also the crop yield. Okay, and also you have to compare the features like you're building, say for example, you are building uh, a simple system to predict yield based on this temperature, humidity, and all. And as a feature indices, you have say maximum temperature attained, minimum temperature attained, and say average temperature attained. So you got all this information from say some climatic sources. There will be some dependency between these two features. So that means they are highly correlated. So in those scenarios, that is also badly affect your model performance. So you may have to discard one of the features. Okay. So all these things you should be keeping in mind when you build, when you select the features. Or you can consult a domain expert to start with. Okay, so that will reduce a lot of headaches. Okay. And also, you can also, apart from the correlation analysis, you can also go for the model performance. And if you find adding any new feature improve the performance, or if you think removing one feature improve your performance, then you can do that also. So the feature quality is very important. And the next one is about the feature engineering. So like I said, earlier days, we do a lot of feature engineering for the image data set, like image of a leaf with a disease. So you have to do a lot of image processing techniques. But right now, we actually focus on deep learning techniques where you can actually feed the entire image assets. It's like you have a color image, so with RGB, and your image is so having a dimension 128 into 128 pixels into 3. Okay, so you don't have to do much image processing techniques to identify the borders. You crop this leaf and all. So you can directly use deep learning techniques to, maybe there are a lot of object detection techniques, frameworks like YOLO and all, which will draw bounding rectangles to the leaves. Then you can pass that to deep learning models. So a lot of things have changed in the case of feature engineering. So deep learning techniques automatically start features. And also the normalization of features are very important because if you are going to use this RGB colors as it is, like you have intensities from 0 to 55, there will be some colors with high intensities, so which may not be good for a model. So you can normalize all those values between 0 and 1 and pass this to model. Okay, so that's about the feature engineering part. Then combining models is the last step. Like if you have multiple models, you can combine and get the better results. We generally call this as ensemble techniques. Okay. So now the last stage is about the model validation. So we have already discussed some of the techniques for model validation, like accuracy, precision, recall, F1, all these things we'll be using for a classification problem. You can draw a confusion matrix, like whether you're predicting correctly, whether the label is correct, or whether the label is wrong and predicted as wrong, and all confusion. Based on the confusion matrix, you can have all these metrics. So F1 score is actually one of the good metrics to measure the classification problem. And you have RMSE and MSE for regression problem as well. And the metric is area under the curve. So all these model validation techniques should be used for your test data set, or you can say the validation data set. Okay, nowadays with the deep learning concepts, the validation data set is actually part of the training data set. They will be, when you build the model, the validation data will be testing your model as together, and maybe you can use a separate test data set to test your model for performance. Okay. And once you find that there is a chance of improvement, you can go for model hyperparameters tuning and improve the performance of the model. Okay. Now, with that, keeping that in mind, now let us look at some of the use cases. So, as I said, there are a lot of scope for agriculture 4.0 in India. And you can see, according to this report, the agriculture market is expected to reach $18.45 billion in 2022. Okay, according to the CA 3.8%. So there is a lot of scope of adopting this agriculture 4.0 with precision farming, lifestyle stock management, with the help of drones, soil management, and all. So if you are going to work in a research problem in this area, and there is chance that you will be getting a lot of funding also. Recently, from the case history, one of my MT student also got funding for one of the problems. It's actually about land classification. Using deep learning, so it will help us to identify the lands that used for cultivation, and to identify the scope for improvement. Like we can identify new lands, or you can also use this as your target labels if you are going to build some kind of a model to for yield prediction and all. Like you can filter out, you can mask out all the croplands from the other like forest or other buildings and all. So this there's a lot of scope for many research projects in this area. And from the data set point of view, as I said, using Google Earth Engine, remote sensing data is freely available now, and it requires a few lines of code to fetch that into your Google Drive. Okay, and weather data is also available through a lot of APIs. You can fetch the weather data information also. And remember, all these data set, they are time series data set. Okay, like when I say time series data set, you can see the weather information, say from February, October, November. Okay, so it's a kind of a time series data set, and you can also build many time series model using this kind of data set. And this geotagging of these smart farms is also very important, and for farm level crop yield prediction or crop monitoring is very important using smart farming geotagging labels. And as I said, from this data set, say for example, you can extract informations like, say, precipitation, temperature, humidity, evaporation, etc. And you can build many different models by using those information. So these are actually fetched from climate sources. And from the satellite data, there are a lot of feature engineered satellite data available. This is like NDV is like a normalized difference vegetation index. LA is a leaf area index. So this NDV and LA and all. So it's like the amount of vegetation. It will give some idea about the amount of vegetation in your image that is captured by the satellite. Okay, and you can map that information to maybe, say for example, predict the type of crop. For example, different type of crops or the yield of crop, etc. So this information can be used. And then there is something like soil adjusted vegetation index, standard vegetation index, known as different water index and all. So all this information, they are actually feature engineered remote sensing data. And you can also do some further feature engineering, like you can take the NDVI ratio and you can go for different crop signatures. So when you look at these figures, you can see that each crop is having different signatures. So these are the extracted features from the remote sensing data. Okay, and you can use these crop signatures for building different types of models using machine learning, deep learning techniques. And once you do that, you can use that information for many business use cases, like banking, financial services, or insurance companies will be looking at this information, or agriculture companies, they'll be looking at this information. And a lot of research projects are also getting patented recently, and there are different patents also happened. Mainly the patents is US patents upon many different types of sensors, and based on that they are developing many decision support systems. So a lot of patents are also happening, and in India also many patents are getting filed. And the ultimate result of this remote sensing data based techniques are, you will be getting pixel level output. Like for example, if the resolution if the resolution of, say, the pixel is 30 meter, you know that represents, say, a farm. If you have a large farm, maybe in acres. Okay, so with this high precision, high resolution, you'll be getting a lot of information corresponding to each farm. Okay, there are other remote sensing satellite with high resolution also. So in that scenarios, you can also get some idea about, say, the block level coconut production statistics, so and so. So all those are the works that is happening around. Okay. Now coming to the case studies. So I've kept three case studies for this kind of agriculture problem. The first one is a leaf disease detection or the identification of weeds using a deep learning technique that is called a convolutional neural network. Okay, so when you look at this figure, you can see that in the first figure, there are different kind of leaf diseases data set. Okay, so as I said, this is a kind of a supervised learning problem. Okay, so I'm connecting to all those things that we have already discussed. Okay, so it is a supervised learning problem, and the images are actually your data set. Okay, you have your samples, all that you have one, say you have, say, 20,000 images, for example, of this leaf disease data set. Okay, so these are your data set, and you also have the corresponding labels for each images, like the type of diseases. So assume that the type of disease is encoded like 1, 2, 3, 4, 5, 6, 7, the different types of diseases. Okay, actually, how these images are actually stored in this kind of problem. Say maybe you can assume, like in your machine, you have 7 folders, 1 to 7. Each folders will be having data of those corresponding disease images. Okay, so you can think in that way. So it will be easy for you to build these deep learning models. Okay, and when you do, you can do some kind of techniques to read the folder names and assign the corresponding labels to each image. So it's a supervised learning problem. You have labels, you have the corresponding disease for each images. Okay. Now, as I said, if you're going for a machine learning techniques and all, you may have to use some kind of feature engineering techniques to extract features, get numerical values, and all. But in the case of deep learning, say the resolution of the images is 227, that is the X and Y, and it's a color image, so the depth is 3. So you are passing the entire image as it is to your convolutional neural network model. So the convolutional neural network model is actually based upon 2 techniques. There's a technique called convolution operation, and there's a technique called max pooling operation. So based on that, it is learning from your image. So again, you can see up to here, there's a convolutional neural network, and when you reach here, you have features extracted by the convolutional neural networks. Okay, so you can see the dimension has changed. Initially, it is 3 into 227 into 227. Now you have 64 into 13 into 13. So there's a depth of 64. That means that many different features it actually extracted from your data. Okay. And we will connect that convolutional neural network to, we flatten the data, and we will connect it into a deep neural network. And this is our final function that we call that a softmax function, because it's a multi-class problem. So earlier we have seen binary classification. This is multi-class, where you have total 7 classes, and you will be able to find which kind of disease it is. Okay, so you do the training, you do the backpropagation, the model will see convolutional neural network model will be learning. And once you learn, you can use the test data. Maybe you say a separate test data available. You feed the test data and see the performance of your model. So when you use this kind of network, you don't require any kind of feature engineering. Okay, so that's advantage. So that is one case study, that is leaf disease detection, and we can use another case study here, that is identification of weeds. So in this case, we have to maybe use any kind of object detection techniques in before this convolutional neural network. So we have to get the bounding rectangles, so where you have this weed information. So for that, you can actually use a technique that is called transfer learning. So transfer learning means you are going to use a pre-trained model, pre-trained model, okay, which actually trained on a weed data set. Okay, so you have a pre-trained model. Now the aim is you get an image, you get this images into your model. So it can be object detection model plus a convolutional neural network, and you identify this particular weed from the image. And once you get this bounding rectangle from this object detection model, then now CNN can actually use which kind of weed it is, okay, with the category of weed. And what is the overall idea about solving this problem? Okay, so here we have identified which type of disease it is. Here from the set of images, we used object detection to find out the weed. We find out which category of weed it is. Now, based upon this, maybe you can take some decision. So that's the final outcome. Like based upon the leaf disease, you can take decision like which kind of technique you need to use to sort it out, or based upon the kind of weed, which kind of techniques that you need to use to remove that weed from the farm. Okay, so that's a decision that you should be making. So that is one of the case study that is using supervised learning techniques, and it's using deep learning and convolutional neural network. Now coming to the next problem, that is pest population counting using RetinaNet. So the RetinaNet is also kind of a pre-trained model, and which is actually pre. So when I say about pre-trained models, it actually works for image data set. So there's actually a very large image data net, so ImageNet, and no, the pre-trained models is trained on such 1 million database, and that will be very helpful if your data set, the problem that you're going to work is having only a very limited data. Okay, so it will help you to identify, as I said, start features from your images. And what you can do is you use this pre-trained data set, and you remove the last few layers, and you retrain from your data set, and so that you will be able to get some better results with the limited data set. So that is one suggestion I need to make. Like if you have a limited data set, if you want to solve, you can go for transfer learning. Okay, now looking at this particular problem, the aim is to find the pest population count. Okay, so this is very important. So here we are using object detection, and we are using network called RetinaNet. Okay, so I'm not going to the architecture in detail because it's very complex architecture. And what is our aim here? It's like if you are able to do the pest counting, and if you use object detection, and if you are able to count the pest. So here you can see in this figure, it's a dense distribution of pest, and here it's a sparse distribution of pests. Okay, so and the aim is to, if the distribution of pest is sparse, you may have to use only limited amount of pesticides, right? Or if there's a dense distribution, so the quantity of pesticides that you need to use, that's a decision that you need to make. So these things are very helpful in a smart agriculture scenario. Okay, so that's a second use case. Now coming to the third use case, there is a technique which is again is a the supervised learning techniques is based on a regression problem, and you have a lot of data available from remote sensing data. So this is NDVI is available from remote sensing data, and you have data from climatic the climatic indices, also the size of land cultivated if it is available. Okay. In India also you will be able to get all this information about this data, and you have a yield data that you can map to. Okay, so what you are going to do, you are going to use these features to map the yield. Okay, and once you have this yield, and based upon the size of land cultivated, you can get the production, maybe the production in tons. Okay, so when you look at this figure, so you can see that these years of data is used for training. So up to 2000, maybe 18, 19 or 20, and you're going to make a prediction of yield in 2020. Okay, and this actually shows the maximum difference that you can be getting when you make a prediction. Okay, so like this is one of the way to use crop yield prediction. That is one technique where you have years of information for to train with, and also you can also convert this data into a time series data. Like usually when we used to sow these crops maybe in the month of June, July, and you'll be getting this harvesting in December if it is a crop like wheat, rice, and all. Okay, so you'll be getting a time series of data of human variables of this remote sensing data. So you hope you know that remote sensing data depends upon the composite period of satellite. Like you'll be getting for 8-day composite, 60-day composite, you'll be getting a time series data. And you can also make an early prediction. So that is very important. So like uh, you have you're going to do the harvest in December, and you are going to make a prediction in August, saying that the expected production or expected yield, say, is 50 kilogram per hectare or whatever it is. Okay, so if you're able to make a early prediction, then you can help these decision makers, like whether they want to import from some other states, like a decision makers, like a district level decision makers. They want to import from other states. If they expect more yield and more production, they can also do the exporting. So the decisions can be made in advance. So that will solve all some of the challenges that we faced in the agriculture. Okay, so that is one case study based upon regression. Now coming to the unsupervised learning techniques, there's case study for finding the organic farming patterns, the different farming patterns taken by different farmers. Okay, so when you look at this figure, you can see that in the farming practices followed by farmers is grouped into 3 different clusters. Okay, and you can see there's these many different data is actually available. So since we have stopped at this particular point, you can see we have 3 clusters. So maybe if you want to have more clusters, maybe you can go and iterate more and get you can stop it from here. Then you'll be getting say 1, 2, 3, 4, 5 different clusters. So what is the decision that you're going to make from this? Here, what you can do is based upon the results, based upon the farming practices, and you can see these red zones, for example. There's nothing meaningful in these colors, but for example, I'm telling. So these red colors, they have low yield. Okay, and this is average yield, this is high yield, for example. So then you can take measures for these particular farms to improvise their organic farming patterns based upon the areas where there is high yield. So these are the decisions that you can make. Okay, that's again a kind of a clustering techniques. So with that, we actually completed our session. Now we'll be looking at the hands-on session, and for that, I request everyone to just go to the link. I have already shared this link yesterday. I'll be putting that in the chat box also. Okay, so you can, if you have already created this Keras, so this Kaggle account, so you'll be taken to this environment. So here you have all these codes ready to be run, and once you run, you'll be able to see the results in the next line. Okay, so this is a particular problem to identify a plant disease detection using a deep learning technique. Okay, so this the model that I've used here. I'm exiting just a second. Okay, so the model I've used here is a convolutional neural networks that we have discussed, and let's see how we can solve this problem using Keras. Okay. If you have any trouble in loading this particular page, please let me know. So you can also do along with me. Yeah, I hope everyone is ready. Okay, so in this particular problem, so let's see how we can do that. Um, so the first cell, this is actually a notebook. We call it a Jupyter notebook. If you have a platform like Anaconda installed in your machine, you can actually run in your local machine also. And in Google Collaborative also, you can upload this Jupyter notebook and you can run there also. But Kaggle, I've used Kaggle because it doesn't take much time for you to actually launch it. Okay, you just have to sign in and get this ready. Okay, so I'll be signing it here. Okay, okay. So I'm not going to run it because when I run it now, it will take time. The model building process. So I can show you all other code. Okay. So this is the code that we use to load certain libraries. So if you want to work with deep learning using Keras, you have to load a lot of libraries for model building to read our images, and also if you want to store the results maybe inside a kind of a binary file called pickle, then you can load that library also. And all these computations are actually performed as an NumPy arrays, and for that we are using NumPy also. Okay, and these are the libraries that is used for building the models, pre-processing and all. And there is a train test script also that help you to divide your data into train and test data. Okay, so once you load that, when you run that, you'll be getting a message like this using TensorFlow backend. So Keras is actually an API, and TensorFlow is the backend which actually will test all the computation. Okay. Now there are some default values set. The default directory for your data set. So it's in Kaggle, and the default directory is already available in this environment itself. So you don't have to do anything. And this is, if you want, you can go and check the directory using the second link I have provided, and you can download it also. And this is the width, height, and depth. It's a color image. So this depth is 3. Okay. And what we are going to do, we are setting some default values like the epochs, the number of iterations you have to do to get the training completed, and the initial learning rate. Learning rate, it actually represents the default values of the parameters of your model. And also the batch size represents how many images you'll be taking at a time. It actually depends upon the environment that you'll be having. So like if you want to increase the batch size, you may have to go for say a GPU. And actually GPU and TPU also is available in the Kaggle environment. And I mean, it's available, say, I think it's available for 34 hours if you want to. So that's more than enough for you to complete this kind of problem. So in this problem, you don't require any TPU, you require only a GPU. Okay, so GPU is a graphical processing unit available, and TPU is actually a tensor processing unit which have a much higher configuration. Okay. And here this code is to fetch images from the directory. You are using OpenCV2, and you're reading the images from the directory. And here in this, in the next code, what you are doing, actually, I said the images are stored inside different directories, and you also have the name of the disease corresponding to each directory. But in neural network, you cannot actually use the name as it is, but whether it is a label or whether it is a features also. Neural networks works only with numerical data. So you have to do encoding. You have to do the label encoding in this case of labels. So if there are features, you have to do the feature should be converted into numeric. But in the case of these deep learning models, or you can directly pass the images, all those things will be actually done by the model itself. Now let's see the different types of potato, tomato, and all these images, the different folders. So we have completely loaded all the images here. You can run all this code quickly. It doesn't take much time. Okay. Now here, as I said, we are doing the label encoding. So we have this many different classes. So these are our labels. So it's a multi-class problem. So based upon the images, we have to predict whether it's a pepper bell bacterial spot, or whether it's a tomato septoria leaf spot, etc. Okay. So these are the things that you want to predict based upon the image data set. Okay. So we are going to do the encoding, and also we are going to do the normalization to your data set. As I said, you don't pass the actual images as it is, you have to normalize. So you divide it by 225 here to normalize the data set. And the next step is to do the splitting of your data. So the data should be split into training data set and test data set. Here you can specify that size of the train. So here 80% of the data is used for training, and 20% of the data is used for testing purpose. That's the way you do the splitting. Okay. Now you have this X train, S test, Y train, and Y test. And you'll be using this S train and Y train. So S train will be used to train, and Y train your label. Remember, in the case of deep learning, you will be taking validation data actually inside your training data itself, and testing can do a separate testing. Okay. So we are dividing into training and testing with 80-20 ratio, and you can see one random state here. It's nothing but the deep learning models. When you iterate it multiple times, you may be getting different results. So this random state is actually making all the initial parameters the same when you do initialize your variables or the NumPy calculations. Okay. So it help you to get the same results when you run it multiple times. So that's a way to work with a deep learning network problem. Okay. And here the next stage is for building the model. Here we are going to use a technique called sequential API in Keras, and these are the different layers that you can add: convolution layers, max pooling layers. You can also see some other techniques like dropout and batch normalization. Basically, they are regularization techniques in deep neural network, and the actuation is used as ReLU. In the end, you can see we have a deep feed-forward networks connected. And last, we have a softmax function, which classifies our leaf diseases into multiple classes. So this is summary of the model, and you can see these many parameters is actually used to build the model. So the more number of parameters means it requires more number of computation. So that's why here we have 5810267 parameters. So we may require a GPU to perform that, and you may not be able to run the same in a CPU. Okay. There are some non-trainable parameters. It's actually part of a batch normalization technique. Okay. And as I said, we'll be using the initial learning rate. We pass it here, and there's a technique called decay also. Like the more when you go for more and more epochs, you should reduce the learning rate so that you will converge much faster. Okay, the Adam is the optimization technique used, and you can see the accuracy metrics is used to evaluate the performance of your model. Okay, so here you can see the training happened in multiple stages, and when you plot this accuracy, you can see the training and validation accuracy. So the blue line shows training accuracy. It's almost 98%, and the validation accuracy is a little bit fluctuating, but still you are getting above 94. Similarly, the loss also, the loss should be minimum. You can get a minimum loss for training, and minimum is almost 0.3 for loss to validation loss. And finally, we can use the test data set to test the accuracy of the entire model. Okay, so we will pass as test and void test to evaluate our model, and as you can see, the test accuracy of this model is 94.728. Okay, so maybe if you want to use this model, you can save the model as a pickle file, and you can deploy that inside a cloud environment or any server, and you can build a web interface where you will upload a new image, new plant disease image, and this particular model will try to predict whether there's a disease is there or not. So you can use IoT, you can use this cloud computing technique, and this model is deployed there, and you can have a real prediction system, plant disease prediction system, automatic detection of disease, or you can say early detection of disease also. These models can be extended into a time series model also, if you want to find the disease in early stages also, which is much complicated. Okay, so that's all about this particular problem. Please let me know when you try to run it. If you have any difficulty, please let me know. Yeah, okay, that's all for my presentation. If you have any queries other than this hands-on session also, you can ask me, please.
Thank you, Sarith sir. There's one query in the chat box.
Okay.
I will read the question for you.
Okay.
It is from Kruba Raji. Currently, I'm doing my research in plant disease detection. What are the future scope in this area? I want to convert my work into startup. Could you please suggest how to convert it to small business?
Okay, so what kind of a problem exactly? I think she can unmute and ask me, because I want to know whether she's working on image data set. Are you working on image data set?
Krubaraji, can you?
Yes, sir. I am working in image data set only, namely disease identification. Almost I have to submit my synapses now. So now I want to convert that into small scale business. So how to do that? Any future scope in this area?
Yes, it's really good to see that you want to convert that into a startup. So basically, if you want to go for any kind of pattern for this kind of a technique, so it actually depends upon the novelty in your work, like whether you have done any contribution, like you have developed a new architecture and you have a new optimizer developed by your own, and you were able to get better performance than existing systems. Okay, so if you are able to do that, obviously you can go for a pattern for your work, and once you have this pattern, then you can really convert that into a industry project also. So they'll be actually looking at your product once the pattern is completed. So I think that will be a better way if you are planning for a startup in this area. And again, if you're planning for a complete package of product, then you have to actually work for the complete system. You have to develop the IoT devices for capturing real-time images. You should be having a cloud environment where you store these images. Okay, it should be completely automated. So if you're able to develop the entire framework, then that you can think about developing as a product also. That's another suggestion.
Okay. Okay.
Sir, there is one more question.
Yeah.
Which from Sneha Deshmukh, which regression model is useful for crop fertilizer requirements prediction?
Crop fertilizers requirement prediction. Okay, so which model? So we cannot say like you go and use this particular support vector regression to get best results. So what you can do is you get the data set, do feature engineering, you do some correlation analysis to find out whether the features that you are going to use in this particular problem is properly mapping to your target value. Then you can go for all the kind of regression techniques. Like you have recently, this random forest regression is performing well. You have boosted regression trees. You can go for support vector regression. You can also have a deep neural network for regression problem as well. So what you can do is you use all these models. You try to do the prediction, and also there is one more technique, like you can go for randomized search of the parameters in this model. So usually all these machine learning models have got a lot of parameters. Okay, so you can go for randomized search. So randomized search will filter out, randomly pick best parameters. Then maybe say you got 10 to 15 parameters. Usually there are 1,000 parameters. You got 10 to 15 parameters. Then you can go for a grid search, which will associatively search for all these parameters into your model, and whichever model is giving you the best performance, you go for that. So that's the issue.
Okay, any other questions? You can unmute and ask if you want. So I don't think there is any other. Sarith sir, can you just turn on your video so that we can take a photo?
Yeah, sure. Okay, sure.
Because we have to document it for the official purpose.
Yeah.
So on behalf of the Electronics and Communication Department, we want to thank Sarith sir for accepting our invitation and being part of this FPT and a very practical session on how to use AML techniques for an agriculture field. So thank you, Sarith sir, for joining us, and we want to thank you, sir.
Thank you, Sarith sir.
Thank you. Thank you, ma'am.
So participants, we will finish today's. We have finished today's session. I've shared the 3 links also. I'll be sharing it in our WhatsApp group also. And tomorrow we have at 9:30 we have Dr. Axel Sikora, who is joining from Germany, and then we have Dr. Srikanth Madhavan from Kabini Tech, and Mr. Srinivas sir joining from IC4, International Center for Free and Open Source Softwares, Trivandrum. And so we are, these are all wonderful sessions. So please join tomorrow. We find that many of you are not joining all the sessions, but kindly join, because as per the Adult Academy rules, you should have 60% attendance, as well as you have to appear for an
80%.
sorry 80% attendance and the 60% marks for the test, which will be conducted on the final day. So we will be basing all the questions from the sessions. So we'll be collecting the PowerPoint presentations from all the faculty and sharing it with you. And we will be preparing an objective type question based on these PowerPoints. So please attend all the sessions and enjoy.
I want to add one more point. ACT people, Adult Academy has asked for the link, and they will be inspecting the experts. They will evaluate, so they can see your participation also. So all the registered participants, kindly join on all sessions. They also will evaluate. The link is given to them. Thank you.
Thank you. Meet you tomorrow.
Excuse me.